Now, it is time to turn to our attention to random processes. Remember, we are the reason for going through this review is we treat the random signal at every instant as a random variable. So, we have learned how to analyze the signal at a particular instant in time. Now, we have to learn to put together this entire chain of random variables and see how we analyze formally. So, that means more complexities are awaiting, but all of that is founded on the concepts that we have discussed until now. Therefore, you should be quite comfortable and thorough with these concepts. Any questions before we move on to random signals? Any questions from that room in 241? Any questions? Okay. All right. So, with this we will begin our journey into the world of random signals and random processes. There can't be a better time than in the evening of a Tuesday. Of course, we will continue our discussion even tomorrow. Fine. So, what we will try to understand before we jump into these standard definitions, like especially the autocovariance functions and so on. Let us now understand what a random signal is formally, what a random process is, and then the notions of stationarity, strict stationarity, weak stationarity, and also ergodicity. Then we will turn to the ubiquitous measure of autocovariance and autocorrelation. Gradually we will build our theory on that. So, to recap again why we are looking at random signals, because whatever I observe will always contain components that are that cannot be explained by known causes, sometimes the causes are also unknown. So, there are two distinctions, as I have pointed out at the beginning of this course, that when you look at a measurement you can think of it to be made up of a deterministic or effects of some exogenous inputs plus a component that cannot be explained by any factors that we know, or that there is nothing in that signal that I can explain using known effects. I have to only actually rely on the history, which is what is the focus of this course, and that is essentially your category number 1, where we build time series models. In system identification we take up the second case, that is where you have composite signals. So, obviously now whether we are looking at time series modeling or system identification, we need a framework to first of all formally represent a random signal, learn how to analyze it, and then how to predict such signals. So, one of the standard definitions that you come across for a random signal is that it is nothing but a function whose characteristics, of course I am referring to a discrete time random signal here, that nothing prevents us from looking at continuous time random signals, but not of interest to us. In practice we have sample data. So, I use xk here, but gradually we will shift to v of k. I will probably change the notation in tomorrow's lecture itself. So, it is a function whose characteristics cannot be predicted by any known mathematical function, and at each point the observation or the value of this function falls out of a probability distribution, which means at each instant in time the random signal is a random variable. Now, it is easier to remember this definition from a prediction viewpoint. For example, we can say that essentially the signal is not accurately predictable. There is no known mathematical function, which means that I cannot predict accurately. It does not mean that I cannot predict at all, we have talked about that. And from a knowledge viewpoint, that is when I am talking of a signal and I am talking of the observations in hand, what I mean by a random these observations being treated as a random signal is that every observation that I have is known with some uncertainty. There were you can say it is known in error, or you can say that there is some uncertainty shrouding that observation that we have. I am not so sure if this is what exactly I should have obtained, I could have obtained something else, that is what it means. So, whichever viewpoint you take, essentially it comes down to the same thing. At each instant the value of the signal is a random variable, right. But the most important thing is that it is an ordered collection, which is clearly reflected in the second definition. Now, you can say that a random signal is an index ordered sequence, and that is the very important part of it. There is a thread that these observations are kind of hanging on to, okay, like the clothes are actually. So, there is this thread in time, and your variables, for now I will use x, but very soon I said we will shift the notation. So, here you have xk plus 1, xk minus 1 and so on. So, all these observations are hanging on to the same thread, and what we intend to do in time series modeling is to see if there is indeed a thread that connects all of them, and then there is something that is not connecting them, okay, which is like the unpredictable part of it. But the fact is that they are all connected by the thread of time. In time series modeling, we exploit the dependencies if they exist. Okay. And once again, this definition says that the characteristics of this random signal at any instant in time, or even when you consider a collection of time instants, they can only be described by probability laws, not, there may be a mathematical function of course, but a mathematical function alone cannot describe the characteristics. So, what are the implications? It means that a random signal cannot be predicted accurately, that we will remember, and at any point the observed value is one of the many possible values. Now, what this means is, if I were to stand at k here, there are many possible values, and this k here, the value could have been here, could have been this, could have been this, and so on. And then there is this dimension of time. So, here is your outcome or realization dimension, whatever you want to name it. A random signal is now in practice, or in theory, it is a 2-dimensional signal. It is a function of the time, or if it is not the time, then space and so on. And then there is this outcome dimension, which is unique of a random signal. In a deterministic signal, you do not see that. What we end up observing in general when I have a time series is some realization at each case. So, here I have this realization, then at xk plus 1 I have another realization, and so on. So, I may end up actually seeing one realization. Of the many possibilities, I end up seeing only one, and we have talked about this realization challenge. So, some examples we have seen, I can skip different time series, we have seen this in the introductory class. Now, we come to the notion of a random process. So, we have defined a signal, now we talk of a random process. Something is generating the signal, right, there has to be a process that generates a signal cannot exist by itself. So, we think of this systems kind of perspective, where we represent the process by a block, which is actually generating these bunch of random signals here. Okay, so, one way of looking at a random process is, it is that process which is generating all possibilities, of course, of which I am only observing one. But this process is actually the ensemble of all possible collections. This is the conventional definition that you will find in many standard and classical textbooks, right. It is the ensemble of the all possible realizations of the random signal. Now, what this obviously means is that a random process or a signal is a 2-dimensional function. Typically, you will find this being written as xn some omega. Well, omega is a symbol we will use for frequency later on, but very often in many textbooks you will see omega being used for representing the outcome, which outcome that you are looking at, or the realization that you are looking at, k. normally we suppress the second dimension, that is we do not talk about the outcome. Anyway, we have only one realization. So, we suppress this and we generally use xk, and you will see these different kinds of notations xk, or tomorrow we may use vk and so on, and occasionally you may also see simply vk. One has to understand whether we are referring to a random signal or a random process, but you will see this slightly different notations. Typically for processes you would enclose in the curly braces indicating that you are looking at all possible realizations. Okay. So, all of this is formalization of concepts, we keep this at the back of our minds. Now, a simpler definition is what I have drawn already. It is that process that generates all possible realization, and what we are doing in time series modeling or time series analysis is trying to understand this process depending on what I want to do. If I want to actually predict or forecast, then I try to arrive at a mathematical equation that will allow me to build forecasts, or if I am actually doing pattern recognition or some kind of a feature extraction and classification, then I am again looking out for some features, all based on this single realization typically, and that is the biggest challenge, right. The reality is that, reality we do not know whether it is actually random or not, but within the framework that we are looking at, this random process generates many possible realizations, and I am supposed to find out what that process is from a single realization. Correct? Okay. Now, some of the things that we want to remember is that a random process always exists. There is nothing randomness about its existence. It always exists. By definition, a random process existed from times immemorial and will exist forever, because if it ceases to exist at some point in time, then it is a contradiction. So, we will assume that it always exists. Engineering perspective is it exists for so long that 100 generations before me and 100 generations after me will never see, wouldn't have seen its beginning or wouldn't be seeing its cessation, right. And again, the process may not be random intrinsically, it is only our ignorance that is making it looking forcing us to treat it as random, that is forcing us to think that there are many possibilities out of which I have obtained one. Now, a deterministic process in contrast is the one process that for which you can fit a mathematical function, there exists and you know it, and there is no ambiguity or uncertainty surrounding its state at any point in time. Now, of course, we will use the words random signal and process interchangeably. There are two questions that we quickly want to visit before we move on, and these are the two common questions that students ask. Is there a process that is absolutely unpredictable? Yes. I have been saying that random process does not mean you cannot predict, but there do exist random processes that are absolutely unpredictable. There are these real life processes that are in some sense unpredictable. It could be in linear sense or in a non-linear sense. Okay. So, given whatever amount of data, you will not be able to predict it. So, you do not want to run into such a problem when you are working in a company, but when you are dealing with an assignment, yes, you want, because then you do not need to build a model. Okay. So, the other question that we want to ask is, does randomness imply no predictability? No, we have already said that it is possible to predict, but we cannot predict accurately, and our goal is to extract the juice, right. In sugarcane, all of it is not juice. Of course, we do eat, but then still throw away what we cannot digest. So, likewise here we want to see if there is juice in the data to extract. If there isn't, then we will throw away the data. We will keep aside the data and say there is nothing, it is too difficult. So, the key point is it is not possible to provide accurate predictions. Now, you will see on familiar websites like Quora or some other website and so on, whether there is a difference between random process and stochastic process. This is like the confusion in nomenclatures. Well, there are some historical things, we will not go into it, but in some parts of the literature you will find this answer that typically random process gives the kind of implication that it is not predictable at all, and whenever there is an element of predictability we would try to label that as a stochastic process. But of course, you know, all there is some historical account, as I said, depending on which country you are looking at. If you, when you look at the history of this theory of random processes, you will invariably run into Russian literature, thanks to Kolmogorov, and then also some literature from you know, Wiener and so on, who was not in Russia. So you will see that there were also political reasons, and then, you know, psychological things and human opinion as to why this word stochastic came up and so on. We will not get into all of that, but you can read that when, for those of you who have said wrong registration, probably go and have the time to read that. Okay. So we will skip this slide on deterministic process, we have talked about it. Now in general, any process that we go out see out there is not a deterministic process, fortunately, otherwise we do not have any job. So the challenge in time series analysis is we have a single realization, and we want to infer the entire process, that is a process that generates all possible realizations from the single one. It should be kind of clear based on the foundations that we have given, and also based on the description, that when we set out to model this random process, what we are actually seeking is to not describe or not to be able to predict a particular realization, because that does not make sense. By chance you have that realization. If you had some other person observing or some other sensor observing, you would have a different realization. So the focus in random process modeling or stochastic process modeling is not on a particular realization, but on so called the average properties of this random process. So at any instant, I am not so much worried about the value per se that I am forecasting, but I am more worried about the averages, more worried about the variability. So the statistical properties are of interest to me more than the values per se. Of course, in forecasting values are important, but when we are modeling, we are more worried about the averages. Now, as we had discussed, in overcoming this challenge, we will be forced to assume certain properties of this random process, and these are the two key properties that we will encounter, which will stay in the background and keep coming up whenever things fail. The first property is that of stationarity. We talked about it. It has got to do with the invariance of the probability distribution, and the other property is ergodicity, which has got to do with how we perform our measurements, how we collect our measurements, how we perform the experiment, and so on. And generally we do not talk of ergodicity if the process is non-stationary. So what we will do is, in the next 2-3 minutes, and then we will wind up, talk about stationarity briefly, and then continue our discussion tomorrow on stationarity, non-stationarity, and ergodicity, and then we will also introduce the autocovariance function. So let us briefly talk about stationarity for the next few minutes. Why are we looking at this notion of stationarity? We have already said that I am going to work with a single realization, which is a collection of observations, and I am going to build a model, right. As an example, I am going to collect temperature data in the morning, let us say on the campus between 6 and 7 a.m., right. Or you can do this, generally students are awake during night times. So you can do this even during night times. Any hour of the day, favorite hour of the day you can pick, and then let us say you sample and you build a model. It is obvious that a model built, let us say over 6 to 7 in the morning, cannot be used. Can it be used to forecast the temperature in the noon, let us say peak time? Why? Something is different, right? Do you think we can use that model? Why? Can you spell out why we cannot use?
The conditions that give rise to the variation
Uh-huh.
will change with time.
What condition?
Like temperatures will be different, of course.
Okay.
There is
So, physically itself the position of the sun is different, right. That gives rise to probably varying heat transfer to earth, correct. So, physically itself you see, but statistically correct, you are right, physically itself the sun's location is different. So, the kind of heat that earth receives is different and so on, and therefore, you expect the conditions to be quite different. But statistically would you be able to describe what would be different between 6 to 7 in the morning and let us say 12 to 1 in the afternoon? Anyone from that room?
The scale of the variable has grown up.
Sorry?
The scale of the variables is grown up.
What do you mean by scale?
I mean,
The range?
values it can.
The range you mean?
I mean, it's shifted, not grown up.
Okay. Anybody from that room? Okay.
So the probability distribution function has changed.
Okay. And why would that change?
Because of the physical process, like maybe at a given time, like it may, if you assume Gaussian at some time, like the mean and variance would have been changed for some other time, like in the morning.
Right.
So like you can't say both of them are same.
Okay, not bad. Well, all of you are trying to tell me the same thing. Thank you. So, all of you are trying to tell me the same thing, but let us put it in a simple way that the set of possible values itself are changing. Like you said, the range is different. You can't, let us hope that is not the case, that between 6 to 7 in the morning you get to, you expect to see temperatures in the range 35 to 40. That would be brutal, right. Already we are facing scorching temperatures. So, we do not expect to see that kind of temperature range at all. When we talk of range, what is the statistical measure that we are referring to? Variance. We are looking a spread of possible values. And then the average also, obviously, when you are talking of range itself being shifted, there is a likelihood, not always necessary, but there is a possibility that the average is also different. So, which means that the model that I have built over one duration of my experiment is not going to be useful, and that may be the case for many random processes. So, we want to know for sure that the model that I build from one set of observations is indeed going to be useful. We will first restrict ourselves to those class of processes, at least we will learn how to model in such situations where the process does not pose such kind of challenges, and that is the motivation for defining stationarity, right. Very often stationarity is confused for steady state of the values. Realizations are not going to reach a steady state. What is going to reach a steady state? The statistical property. So, you see that is what exactly I spoke about earlier. When we speak of random processes, we are not talking about realizations per se. We are frequently referring to the statistical properties. Here, as came from the answer from the other room, we will fix initially, we will come up with this idealism that the probability distribution should not change with time. So, if you look at these examples here, 3 examples, on the left side you have, that is for the figure labeled stationary, it is a tree ring data, the number of tree rings that you can actually get from trees. Is it stationary? How do I say that? I mean, you should not believe me. I am just saying from visually there is nothing that is telling me that is non-stationary, but that can be quite deceiving. Let us think of it as an example of a stationary series. There are formal ways of determining whether some series is non-stationary or not, and so. And then in the center you have a figure, you have a time series which is so called harmonic. It is a harmonic signal in the random world is nothing but a periodic signal. On the face of it, thinking of a random signal as periodic seems to be contradictory, but do not try to apply the definition of periodicity in the deterministic world straight away to the random signal world. Remember, we said for random processes we do not really meddle with the realizations, in the sense we do not really work with the realizations, we work with the statistical properties. So, now you should be able to guess what periodicity means in the random signal world or the random process world. The statistical properties have some kind of a periodicity, not the realizations, and we will talk about it later on. And then on the extreme right you have a time series which is the airline passenger data. You will find this everywhere in many of the time series texts. This series is an example of a non-stationary signal. You can see clearly what kind of non-stationarity do you see. I mean in other words, which statistical property do you see changing with time? Mean, variance, both, right. The set of possible values seem to be changing, there seems to be a shift in time. Now, having said this, this is not straight away going to give us the definition of stationarity. We still have to be more formal, but we will first understand that stationarity means some kind of steady state on the statistical properties. To begin with, we will say all statistical properties, meaning moments, should remain invariant with time, and that can only happen if this joint PDF, this is the formal definition that you see, and with this we will end today. So, this gives rise to the notion of strict stationarity. It is a very ideal kind of definition. What is it saying? The joint PDF. Why are we looking at joint PDF? Because we are going to analyze a collection of observations, right, a set of observations. So, we want to say that this joint PDF of the n observations that I have collected, does not matter, I begin at T1. Look at the statement, it says there are two things. The joint PDF should remain invariant with two things. What are those two things? When I start collecting and how many I collect, right, for all t that is shifts in time and for all n. Although I say for all t and for all n, it is understood that it does not matter where I begin, right, and it should not matter as to how many observations I am looking at jointly, which means it should be even valid for a single observation. Every observation should fall out of the same probability distribution. Imagine that at every instant there is this big bag of possible values, all kinds of colored balls, whatever you want to imagine, but there is this big bag of possible values, and that the possibilities and their distribution should not change with time. Don't you think it is too stringent a requirement? It is. I mean, we do this kind of idealism, we adopt this kind of idealism in every subject. In thermodynamics, we begin with an ideal gas, but there is no ideal gas, correct? And in every situation, when you get married, you think about all idealities. You soon realize there is nothing like that. Okay, I do not know if some of you already realized, but anyway, so this kind of idealism is necessary to get into this world of random signal analysis, and then slowly we will relax this. We will relax this condition, recognizing that this is too stringent, but it is good to start with this. We will say, I wish the process was like this, but it is not, right. So, tomorrow we will talk of more relaxed requirements of stationarity and then move on to ergodicity and autocovariance. Thank you.